So what I want to do now is go through, we'll start with the assignment that was given to you. This assignment should be relatively simple, but we'll go over it just so that you know the materials. Then we'll switch to showing you some codes for PCA that you can use using, that you can do using scikit-learn. After that, we will move back to finishing the last portion of the matrix decomposition module. There's an assignment for that module, but I'm thinking that I won't be here tomorrow, so we'll just walk through the assignments today to make sure that you see what's going on, and then you can always do that on your leisure time over the break, over this evening. And then after doing all of that, if there is some time remaining, I would have come to the end of the material that I had prepared specifically for this program. But there's a topic that's of interest to me, which is causality. And so we'll talk about, if there is time remaining, I'll talk about causality. Because a lot of times, at least in data analytics, we want causality, but we get correlations or we get association. And so there is now several techniques that are coming available that are trying to get at causality even when the data was not collected in a causal way. And that's an important topic. If we have time, we'll get there. Okay, let's start off with the first piece, which is for the support vector machines. I want to look at the assignments that I gave you. And let me see if I can make this a little bit bigger. Zoom. Okay, maybe I can't make it that big. So this one. So let's start this one by one. So first question we basically answered in class. True or false, in training a support vector machine, it's generally a good idea to scale all input variables so that, for example, they lie in some fixed interval or so that they all have the same mean and variance. So this is, you can rescale things very easily by subtracting the mean if you want, that becomes a zero mean, and then divide it by the sample variance so that its variance becomes 1. So in class we discussed yesterday that in general this is a good idea. The reason is that many of the SVM techniques rely on inner products, or they rely on some kernel that is defined from the inner product, such as the Rbf kernel, polynomial kernel, and when different elements that are contributing to this inner product have very different scale, then some variables might start dominating. So it's always a good idea to rescale. So the answer to that question is a true. I'll come to this one. I'll show you. Question? Yes?
Here, why if we convert -1 to +1? Sorry? Rather than 0, 1, use sigma.
Yeah.
If I convert to -1 to +1,
doesn't matter. It just comes standard. So that's why I said they lie in some fixed interval, or they have all the same means and variance. It's not really specific that the mu should be 0 and sigma should be 1, but they should be all of the same scale. Whatever is convenient to you. If everything lies between -1 and +1, that's fine. If even 1 is not necessary, as long as you get the scale right, everything should be fine. And in most solvers, even in scikit-learn, there is an auto scale function that is already put in. So they would automatically scale things. I often advise not to use that auto scale function because then you don't know what happened in the process. But if you're just doing some exploratory data analysis, just turn the auto scale on. That way at least you're going to see whether there is any benefits coming from that particular methodology being used. But after that, it's just a matter of making sure that all variables are at the same scale. That's essentially what you're looking for. Yes?
Scaling is I know.
Yeah.
But like for a regression problem or something, so this was a confusion. Always we try to scale all the input variables.
Yeah.
Because they are only they will be getting.
Yeah.
But is there a need to, somewhere is a need, or it is a need to scale even an output variable?
Absolutely. In here, for example, if the dynamic range of the output variable is huge, sometimes it's and it is non-negative, let's say, then doing log scaling sometimes ends up becoming very good. But one thing to keep in mind is that in some sense, scaling the output, it's like changing the link function. right? So if you do the output scaling, that's almost like you're taking the regression and changing the link function. So if you use generalized linear modeling instead of just linear modeling, some of that is already taken care of. But absolutely, the answer to your question is, the way you should think about it is that there is an underlying truth that we never get at. We are trying to approximate that underlying truth using some models. And we are trying to get at linear models. And the reason we like linear models is that interpreting a straight line is very easy. Interpreting any kind of curve, however nice it might be, like even if I show you a curve y is equal to x squared, and I ask you whether it's x squared or whether it's x to the power 4, it's very hard for humans to immediately eyeball it. Straight line, on the other hand, is easy. So now when you're trying to get to straight lines, you want to help yourself as much as possible. And if by nonlinearly scaling the inputs or nonlinearly scaling the outputs, you end up getting straight lines, now you discover relationships which are very clear. So that's the art part of some of this data analysis as to what exactly works. I did not cover a module that I usually teach before we get here, which is regression and classification. There we spend a lot of time trying to do scaling. Yes?
Actually, if you are looking in the objective function of the SVR, they are like weight is attached to every feature of X, right?
Yeah.
So if you are taking linear SVR, is it necessary to have do scaling for that, because weight will everything take care of that?
Yes, but the thing is that one of the things that you want to make sure is that you don't want the weights to become too large or too small. So what I mean is, you're absolutely right. If you just do linear scaling, it should work. If you do kernel, then there is a little bit more of a problem, because now you're taking the kernel of the weight vector with the x vector, so it's not very clear exactly what is going to happen there.
I saw that Rbf function is also similar like our normal distribution equation.
Yes, so RBF you definitely need to scale. There that argument fails. Your argument will fail for RBF because if you let me actually bring up since this question was asked, let me bring up this, where did it go? Okay, if you look at this might be as well as a good place to start. You have W transpose X. So your argument is that, look, if X is not scaled, if it's not centered or scaled, I can automatically rescale the W by the same amount, and therefore I will end up getting the plus B over there, right? Now, on the objective function, that is true. But if you look at the constraints, right, what happened over here? Look at the next line. Now we can rescale W and B such that without changing the decision boundary. So arbitrarily, I have chosen, where did my thing go? I have arbitrarily chosen that W transpose Xi plus B must be greater than or equal to 1 for all positive samples. So right here, I've already put a scaling on W. So I have restricted myself that I can't arbitrarily scale W because this has to hold. So there is a constraint that's been put, but even with that constraint, you can still make an argument that W still has a lot of freedom, that it can take care of the scale of the Xi. But if you look at what happens to the Rbf kernel, in the Rbf kernel, the way you use this are two different data points. There is no free variable here anymore. And when that happens, now if you look at this Euclidean norm, and let's say this is what we were discussing yesterday, one component is of the order of 10 to the power 8, another component is of the order of 10 to the power minus 8, right? Let's say. Then when you look at this norm, the 10 to the power minus 8 guy will just get washed out. Its contribution to this norm will be gone. And I have no way of rescaling it because I don't have a W vector that I can put here which would scale that component up by 10 to the power 8, scale that down by 10 to the power minus 8 so that everything becomes rescalable. So the moment you go to kernel space, you lose that freedom of rescaling using the W vector because, where did we go? Because what happens is that the actual W vector that you choose is an alpha, which is an alpha star over here, which is outside the kernel. So I don't have the ability to rescale elements of Xi directly anymore. So when you're doing kernels, for sure you should rescale. If you're doing linear, you can get away with it. But then in many of these cases, right, you want all of these processes to be brain dead. You don't want to remember to yourself, oh, I'm doing linear kernel, therefore I don't want to scale, or I'm doing Rbf kernel, therefore I want to scale. Scaling doesn't hurt you, so might as well scale and live with that, as opposed to keeping cases in your mind. This one I'll show you in a little bit. I'll show you the solutions and I'll show you the code. It's a pretty trivial exercise to do this. This question. Again, this one, the next question is a little bit more complicated and I'll get into it. So suppose you have successfully trained an SVM with 10,000 training inputs. Okay? And a Gaussian kernel where C and sigma, so we were thinking in terms of the scikit-learn has gamma, I'm here having sigma here, were selected using cross-validation. Okay? You are now given an additional 40,000 training points. So you wish to retrain your SVM using the entire 50,000 rating points. So there's 10,000 from before, you found your C and sigma from there, and then you wish to retrain your SVM using the entire 50,000 training points that you have now. However, you wish to avoid the heavy computational expense associated with repeating cross-validation exercise, so you therefore simply choose the SVM using the values of C and sigma that you obtain using 10,000 training points. Okay? Do you see any potential major problem with it? If so, what it is? So what has happened is that you had 10,000 points to begin with, and suddenly you got a data dump of another 40,000 points. Should you redo everything? Should you get a new value of C and sigma? Or should you just live with the 10,000?
Those 10,000 points are from population that 50,000 points?
No. Yeah, the first 10,000 points are the 50,000 points.
Sample from the population that 50,000?
Yes, same thing. So what we are doing is that, so that's a very good question. In fact, the answer will be constructed using this. So let's say that there is some underlying distribution and the points have been sampled according to this underlying distribution. Both the input points and the target, the classification value for that has been sampled from this underlying distribution. First time I gave you 10,000 points from this underlying distribution, and then I chose another 40,000 points from this underlying distribution and gave it to you. Okay? Now you decided to equivalently, you can think as if what you did was you generated 50,000 points, threw away 40,000 points, and trained only on the 10,000 points. Is that a sensible exercise?
If we take sample, because it is a sampling technique.
Exactly.
So we are picking up the sample from, if it is n dimension, different point we are picking.
Yes.
So my understanding there will be no such difference. Maybe some accuracy of the parameter needs to be changed.
Yes, but remember, what are we learning here? So, good question. I mean, let me rephrase your solution, right? Suppose n is 100, the dimension of the problem is 100. So think about the answer in that case. Take the other case where n is say 10,000, n is 1 million. So let's understand how will your answer change if I change the dimension of the underlying space. So let's take n is equal to 100 first. So the underlying space is just 100 dimensional. So the data vector is 100 dimensional, and the output target, let's say, is +1 -1. So let's make our output very simple, right? Now in that case, I still have this exercise. Somebody sampled 50,000 points for me. I decided to take only a subset of 10,000 to train. Do you think it's okay? Now compare your answer when n is equal to 100 to n is equal to say 10,000 to n is equal to 1 million. If you're increasing the dimension, what should you expect will happen if only you took 10,000 points out of the 50,000 that you had available to you? So remember, I mean, the way to think about this is ultimately what you want C and sigma to do is you want to find the C and sigma that works for the underlying distribution. Underlying distribution, because the test set is going to come from the underlying distribution, whatever that distribution is. Because if the test set doesn't come from the underlying distribution, we are dead anyway. So the only hope that we have is the training set and the test set are coming from the same distribution. So this C and sigma that we are trying to do is find the best for the distribution. And what we are trying to do by getting the samples is approximating the distribution. All right? So if you have dimension n is equal to 100, 10,000 points seems reasonable. it seems to give me reasonable coverage. So by 10,000 points, I would be getting a C sigma which is reasonable, and therefore doing this redoing of another 40,000 points is not going to be a huge difference. I go to 10,000. Now effectively you have 1 point per dimension. Right? You've got 10,000 points. You've got a 10,000 dimensional vector. You effectively have 1 point per dimension. Now you're getting into a point where from 1 point per dimension to 5 points per dimension, it's starting to make a huge difference. And so the way to think about it is that these data points are trying to empirically approximate the underlying distribution. To the extent that these points are enough to approximate the distribution, you're fine. And the moment you start getting into a situation where this is not the case, you want to use as much data that you have available to do the training. So in general, do you see any potential major problem? It depends on the dimension. The right answer would be it depends on the dimension of the problem. If the dimension is 2 dimensions, even 10,000 is probably an overkill. If it happens to be, I don't know, of the order of 10,000, maybe we want the extra 50,000 and so on. So this is a more qualitative answer. All right, the next one. This one is mathematical, so I'll show you the tricks as we go along. I'll show you the solution here. Let me actually just go to the solution so that I can, but before I go there, I will show you the code for the second problem, and I will coordinate with, make sure that these get to you. I'll coordinate with Raghu to get it to you. Zoom in. So here is basically the code that one can use for solving the second problem. This is, we were working with the cancer data set already. This shuffle split is an algorithm that is available within sklearn that can generate as many splits as you like. So what I've done here is I've generated 10 splits of size 0.2. So test size is 0.2 and the training size is 0.8. This is some random state that you can give whatever you feel like it. I've defined here a linear kernel with C equal to 1. And then all I'm doing here is I can iterate over the splits that I have. So within scikit-learn, you don't have to generate them yourself. The training index and the test index are already given within this split. So cv.split cancer data. Here I'm specifying that you use this splitting technique on the cancer data. It will give me an index. 80% of it will be training, 20% would be test. I subsample the data, x train, y train, x test, y test. Fit the distribution, predict the distribution, and here are all the various accuracy metrics that one can use. You can use accuracy, you can use precision, you can use recall, you can use the minimum of all of them. So this is what I've done, the minimum. I'm taking the minimum of the accuracy, the precision, and the recall, and calling that min score. And once you've done that, here are just loops of what happened over here. And then you can figure out exactly what is going to happen. So this code is simple, but let's go back to this question here and see whether we can argue as to what's happening with that question. There we go. So the first piece, construct a linear SVM with C equal to 1 on the cancer data from sklearn, split the data into 70/30, compute the performance, repeat it 50 times. So the n was 10 in my case because I was just lazy. You could make it 50 and it will do exactly the same thing. You can compute the mean and the standard deviation of the test set performance. You repeat the part B for 50%, 55%, up to 95%, and plot the mean test performance together with the 95% confidence intervals for this performance against T. Okay, so what do you think this will do? And well, in the solutions, I will show something that my colleague with whom I co-teach this course had done it in a previous running of this course. So let's just hypothetically argue what is going to happen here. So what's happening here is that the test set value, so this is the proportion of test set, so 50% was left as training, 50% as test, 55% as training, 45% as test, 95% as training, and 5% as test. So as you look at the performance of what is going to happen for this different test set, what do you think intuitively should happen? So if you have, let's start with this extreme. If you only took 50% of the data points as your training set, and now you want to predict what is going to happen in the test set, and you are going to do it 50 times, what do you think would be the performance? I mean, it will turn out that this particular data set is actually very easy for some reason. Do you think, so let's compare 50% versus 70%. Where do you expect better performance? 70%. Why is that? Because I'm getting a better representation. The same idea that we were talking about in the first problem. I'm getting a better idea of the distribution because I have more points in there, and therefore I'll end up getting in the test data I should start getting a better performance. I have a better understanding of the classifier, and therefore out of sample I should get a better performance. Now let's push that idea, 70% versus 95%. Overfitting will happen, and therefore what will change out of sample?
It will learn more.
So it's good, right?
On the test it might.
Why will it perform badly?
It hasn't seen the data and it has already trained itself with whatever the data, 95% data.
Okay, so that's exactly the point, right? So what I'm trying to push you is to understand why would this phenomena of overfitting happen. So you're right that you expect that at 95 the performance would be worse than 70%. Why is 70% a magical number? Who knows? It just depends on what the distribution is. But as you keep on going to 95%, let's argue. So it has seen a lot of data points. Let's assume that the test distribution is also coming from the same distribution. Right? I'm not saying that the test is a different distribution. It's coming from the same distribution. Why are we claiming that the performance on the test set would be worse?
Because if you consider convex solid, the test data set may not consider that endpoint in convex solid.
But that should happen at 70% also.
But 70 for when because it is the random source of few data points that is existing in train.
Yeah.
That may not exist in that is existing in test data.
Yeah.
Convex solid may be few data because we are taking random.
Yeah, absolutely.
Few data points that is existing in test data.
Yeah.
That is not available in train.
But at 70%, your argument is even stronger. Many data points that appear in test are not available in train, right? When you have only 70% of the test data with me, many points that might be there, more points in test may not be available in train. So I'm just trying to push the.
I use the new another data set because we are using for future predictions.
No, but what I'm saying is that the new points are from the same distribution. It's not a different distribution. I'm just trying to push you to argue why. So your argument is that I will not have seen the test points within my train, and therefore I might end up performing worse on it. But when you have 30% left over, there are more likelihood of not seeing points in the test, right? In the train.
No, I am not telling that. I am telling when I am doing, I am fitting a model.
Yep.
Now I am using test data set.
Yep.
Now test data set has few points that does not exist in train data.
Absolutely.
So what happens when I am using that model for test data?
Yeah.
So that error will be maybe higher than that train data.
Okay, now let me use this argument, your argument back at you. I have 70% of the data. Let's assume that the few data points that were left over are in that 30% still. Right? So I have 95% I had first in my test set, 5% was left over. Now consider a situation where I expand that 5% to 30%. I leave the old points there, I expand it to 30%. Now the 70% of the training set is there. That bad points that you were talking about still exist. Now I train it on a smaller set. So therefore the performance should be worse than the 95%. I'm not saying that your argument is incorrect. All I'm trying to do is I'm trying to make sure that you understand where that argument is coming from. There is one little missing piece in your argument. There are two issues there. One of them is absolutely right, what you're saying, that you miss points. But you miss points all the time. But there is another thing that is there, that 95% ends up causing problems.
Because there is noise in that data, so that also gets modeled and then the parameters get affected because of that. So,
Yes, okay, but somehow that same noise must exist even on the test. Because we are saying that both data points are coming from the same underlying distribution. So if the underlying distribution is noisy, so be it. I want to represent that. So there is a little piece that's left over. I mean, you guys have got most of it right, but there is a little piece that is actually very simple that is missing.
Error will be more.
Why will it be more?
In the test data.
Why? That's what I'm after. So one idea that you guys have is absolutely right. When you try to train too much, you have a situation where you may have modeled noise. And what happens when I have only 5% of the test? So you have modeled, so let's take the case where you have modeled the distribution nicely, but you only have 5% samples from that distribution in the test. So what is going to happen when you only have a very few sample points from the underlying distribution? The noise in the test set compared to the noise in the training set, what will happen to the noise there? If you have very few data points? Much higher. So the way to think about this is you have the same underlying distribution. If they are different, it's gone. The underlying distribution is the same. We are taking a small amount of it, some reasonable amount of it, to model what is going to happen within sample. Now I want to model the performance of this classifier out of sample, assuming that the data points are coming from the same distribution. If I don't have enough data points out of sample, the out of sample performance of this classifier is going to be very noisy. So when you look at what is going to happen out of sample, there are two components that are coming in. One is this overfitting component, which all of you discovered, which is very good. There is another component, which is that even if you didn't overfit, even if everything was fine, when you look at the performance out of sample, the number of data points have to be reasonable for you to be able to say that I have a good estimate of that performance. So when you go to the limit of 95%, where only 5% of the data set is left remaining, the number of data points that are left over aren't enough to be able to capture that variability well enough. So you will see the variance increasing. So if you look at the plot, I just want to make sure that you understand that when I was trying to push you guys, I was not saying the overfitting is a bad thing, but there are two things that are going on, which is here. So out of sample performance looks whatever. We expect the mean error rate to decrease as we increase t. So here's the story. The code for, let me actually make it a little bit bigger so you can see what's going on. This was an R code that's not there. We expect the mean error rate to decrease as t. This is because we should get better classifiers as we give ourselves more data to train them and use cross-validation to control overfitting, because I can keep on doing this C in one, I can potentially control overfitting. However, with large values of t, we also leave ourselves little data to estimate their error rates. We can see some improvement for the mean error rate for smaller values of t, but as t becomes larger, the error rate estimates become noisier. It's difficult to say whether the mean error rates actually improve. On the plot, you can see that the confidence interval become wider and overlap. So basically, as you start going to 95%, the box plots and the intervals end up becoming much larger. So around here, you end up around 70%. The mean is sort of not changing by much, but the noisy part becomes much larger.
Invariant state of that.
Yes, so it's just, I'm looking at the mean.
Part is less, bias means different, actual minus target.
Yes.
Variance is increasing.
It's increasing. So since I don't know what actual is, if the variance is this large, I have no way of knowing what is going on. So that's why you need to balance both.
But if my data set is huge enough,
Yes.
if the 5% itself is sufficient to cover the variability in the distribution,
Yes.
then probably it should asymptotically increase as we to 95%.
Correct.
That I have a huge data set.
Yes, but one thing to keep in mind is that one thing that is sort of hidden here is that you have to make sure that you use cross-validation to make sure that the overfitting doesn't happen in the test set. If you're very careful about making sure the overfitting doesn't happen in the test set, then the 95% may work. What is the point of this exercise is that this 95% number is irrelevant. The point that I want you to take is that if you take too few data points within the training, you have the problem that you don't train the classifier very well. If you leave too few points for testing, you have a problem that you will not be able to characterize the performance of your classifier. As a result, you have to balance the two. If, for example, you use a very simple classifier, but you have a huge data set, then the leftover data points might be sufficient to characterize your performance of your classifier. On the other hand, if you used a classifier which is very complicated, then you need to have enough coverage over the entire space to be able to characterize the performance of the classifier out of sample. So 95% is sort of done to make sure that this particular data set gives us the performance that we want. For other data sets it will be different, but just keep in mind that you don't want to keep too many into the test, but you don't want to keep too few as well. Okay? Yes?
So what should be that ideal approach that you're looking for?
Like I said, there is no ideal. Yeah, so I use 70-30, maybe somebody likes 80-20, there is nothing really magical about it. Yes.
So in cross validation, we use like 90 to 10%.
Oh no, so cross validation is within the test set. So that is different. Here I'm showing, or think of this as the validation part. How much do you keep for validation? Within the test I can do all kinds of things to get my parameters. It depends on, again that's an art. The same story, if you do 90-10 and you want to rely on the mean performance out of sample, that is you get 10 data points, you've left only 10% of your data to sample things, again it's not clear that averaging over 10 is a good idea. So the same question can again be asked there. Raghu, question back there?
I have a question. Right. See, for example, we are repeating with 75 and 25.
Mm-hmm.
And we keep repeating, like pick up a sample, do the testing, and then cross validate.
Yep.
And again, take it from the same sample, repeat it. So the variability of the tests,
Mm-hmm.
would it also change? Because if you are saying that if I take a small data set for the last stage, 5%,
Yeah. Yeah.
and if I keep repeating, so
Yeah.
obviously the variability would also start decreasing as I take more and more samples. Each time 75% I am taking.
Yeah.
I'm trying to find the general sample statistic for that 75 immediately.
Yeah, so okay. So let me just clarify something. In the experiment that we did, what was asking people to do was take 75%, get a classifier on that 75%, test on the 25%. Get another sample of 75%, potentially generate a new classifier, and get another 25%. Now I'll repeat this. If it so turns out that the number of splits is so large that every data point has been covered multiple times over, then you will run into trouble, because in some sense you don't have any independence left over. But if in this particular example, I think there are about 700 data points approximately. I don't remember exactly, but it's of that order. And the number of splits taken is 50. So the probability that you will cover many data points many times over is low. So if your question is that if I keep doing this and doing this and doing this, then it's almost like nothing is random anymore, because all the randomness has been covered very nicely and it will not work. So you have to make sure that the number of splits or the number of tests that you run are a small fraction of the total amount of data points that you have.
Yes. The reason why I'm asking is that, say for example, for multiple linear regression or something, I have a data set, but I want to basically predict it for a large sample, when we're almost going towards the population.
Mm-hmm.
So if I concatenate it,
Mm-hmm.
like increase the overall size, so wouldn't the concept of central limit theorem be more overwhelming in order to not, like say for example, I'm taking an extreme value distribution, and then I increase the sample size, concatenate it many times.
Yeah.
And then I do these tests,
Yeah.
run the regression.
Yeah.
So wouldn't central limit theorem come into the picture and normality would start?
Yes. So what you're basically saying is what you're saying is if I increase the number of test set, I should start getting performance which is close to the population ideal, which you will get, which is the first part. So there are two potential errors here. Assuming that the test set is also going to come from the same distribution, the more points that you have and the better you have actually penalized your regression enough to make sure that things don't go bad on your test set, then as you increase the size of the test set, you are likely to see which much closer to the population performance. That's great. Now you look at the test set. The test set has very few vectors. those very few factors may actually be a very extreme sample from the population mean. And so when you evaluate your performance onto that test set, you might actually get a bad performance. You have learned a classifier that is going to work for the population distribution. You have the empirical distribution which is very far away from the population distribution. Therefore, your performance there could be pretty bad. So you need to balance both. You need to be able to have enough data points to get to population, but you have no way of knowing whether this classifier is very good. The only validation that you have is to test it on other data points which also need to be close to the population distribution. Otherwise, you will erroneously declare that you could erroneously declare that classifier is bad. So that is why you want to keep reasonable amount in tests, because if you have a small sample in the test, that small sample is going to be far away from population. And so you need both of them to be representative, judicious balance of the two.
The reason I am asking is nothing to do with the preference. For example, in multivariate regression, there is a balance loss function where you have the error of prediction as well as the error of estimation.
Yep.
So you want to basically balance.
Yeah. Bias variance. This is bias variance trade-off.
So when you are basically giving the weights to these two errors,
yes.
One set is you are trying to predict the betas.
Yes.
And then using the beta hats, you try to basically predict the y hats.
Correct.
This balancing which is done.
Yes.
The more you give the weights here and there.
Yes.
Basically, for a large data set, it turns out that normality starts ruling in a very big way. That's what I saw. But I have not done all these things.
Yeah, so in some ways, if you're trying to do regression, life is a little bit easier because you're averaging errors. Here, you're doing classification, so life becomes a little bit harder. But as the comment was being made by somebody else, that if you have a very huge data set, even for this, it should not make a huge difference. The point of this exercise was simply to get people to think about the fact that there are two kinds of errors. One is the prediction error, and the other one is the classification, learning the classification error. And both those errors have to be balanced. Okay. All right, so.
How do we deal with these types of problems when the data set itself is very small?
Life is tough. You do the best you can. I would say that you basically hope that, okay, let me actually take it back. When the complexity of the classifier that you should use should be commensurate with the size of the data set. If the data set is small, then you should not try to use too complex a classifier. And if you're using a simple classifier, the way to think about this is that like with this discussion, we were talking about the population distribution. There is a population, you want points in the population distribution for train and for test. Now, what does it mean to have population distribution? So if you have a very simple classifier, then many different population distributions will give you similar answers, because the classifier is not complicated enough to detect very small changes in the population distributions. So take about a classifier that's just a straight line. As long as if you have enough weight on that side, enough weight on this side, you will discover it. So when you have very small data sets, you can pretend as if this has been sampled from a population distribution, but it could have come from many different population distributions, because this data set is so small that if you think about the inverse problem, which distribution could it have come from? Not that we'll ever solve that problem. Many distributions are candidate distributions. So I want a classifier that works for all of those candidate distributions reasonably well. And the only way you can make that happen is to have the classifier simple. And so if you use a simple classifier, you can get, so for those of you who have done statistics, there is this idea of non-parametric statistics, where you increase the complexity of the classifier based on the data points that you have. There is a similar notion here, although people haven't formalized it in machine learning as to how should you increase the complexity, but that idea still should be there, that you can't have too complicated a classifier when your number of data points are low, because you won't be able to validate it in any reasonable form.
Same holds true for regression.
Regression is true, but it's okay. Regression with variable selection, the same thing holds true. If you have a fixed number of whatever features, then it's okay. But if you want to do variable selection on top of or do feature selection on top of this thing, then you need to make sure that the number of features that you pick are commensurate with the data points that you have. If you pick too many features, then the confidence intervals on the betas are going to be so large that you won't be able to really get anything reasonable out of it. So a similar story exists there.
Is there a thumb rule to say we have to take 15 times the number of features that we have, the minimum data set?
Yeah, I use 10, but that's just my rule of thumb. When I teach Monte Carlo sampling in my university, I basically tell them per dimension that you're trying to estimate, have 10 points at least. Why 10? I have no idea. It's let's just put it this way, that if it's closer to 1, then you're definitely out. You're closer to 100, you're pretty good. Somewhere in between is where you probably want to be. Is 10 the right place, 15 the right place? No idea. It also depends actually on the distribution itself. As Raghu was pointing out, if the distribution doesn't have heavy tails, then maybe 10, 20 is okay. But if it has heavy tails, then even 10, 20 is not going to be there, because that 10, 20 you may not be able to capture the extreme data point, but in the test set you'll get that extreme data point. So you may not be able to get good coverage. So it depends not only on the classifier, but it also depends on the population that you have. All right. More question? Yes.
So suppose we have a highly unbalanced data set.
Yes.
Like 80% for one class and 80%
Yep.
for another class.
Yep.
So how should we approach for like splitting and all those things?
No. Here we are assuming that you do similar kind of splitting. So if your population data is of that, you get similar kind of splitting out of it.
We might learn good for one class and not for one.
No. When you sample the thing for training and test, you make sure that you don't randomly pick such that you get 95% of one class and 5% of the other class. You subsample. Make sure that you get good representation of both classes. If it so happens that you don't have the other class, then at some point it comes back to the same question of, if you don't have enough data points, there's only so much you can do. You really need, the way to think about it is that you are trying to generalize something to the underlying distribution using the samples that you have. And if I asked you the question that the underlying distribution is complicated, you have very few data points, now what are you going to do? There is nothing you can do, because your knowledge is just that data point, unless you have some other knowledge on the side. Maybe you have some knowledge that certain features are not going to be important, or you have some knowledge that certain features are going to be important. Then this side information can be used. But if you have nothing else available to you, and you have a disbalanced data set, and you have very few points, then you pray that things work. And then, okay. So this particular problem is more of a algebra exercise for you to work out. This is the main trick I will. So let's see how we want to do this. I'll just show you the trick A, and after that everything else basically uses that trick to do various kinds of things, and you can look it up in the solution. So this is just a trick this is an optimization trick that I wanted people to know, which is, if you have maximum of absolute value of y minus epsilon and 0, and I want to be able to write it in a different form, which is that last form, I can write this as the maximum. First piece is u going from 0 to 1 of u times the absolute value of y minus epsilon. This is the trick that we saw yesterday many times over, that if y minus epsilon happens to be greater than 0, then I'll pick u equal to 1. If it happens to be less than 0, then I'll pick u equal to 0, and I'll get that maximum. Now, I want to remove the absolute value sign. U absolute value of y minus epsilon u. At this step I have not done anything. Now what I want to do is, I want to look at this summation, and I want to be able to say that if y is positive, I know that u has to be positive. When y is negative, I want u to be negative. So instead of taking the interval between 0 and 1, I take this maximum between -1, 1, uy. Now in this particular case, if I allow for -1 to +1, whenever y is positive, I'm going to take u positive. Whenever y is negative, I'm going to take u negative. So I'll take care of this product. But on this direction, I have a problem, because here epsilon has a fixed positive number, and I don't want this sign to switch based on whether u is positive or negative. So I put minus epsilon times the absolute value of u. And you can check that this optimal solution will be exactly that. If you look at so take the case where y is positive, then I will take u positive, and then this will give me exactly the same number. When y is less than 0, then I will take u negative, but over here I am still having u positive because I put the absolute value of u, so this will not give me a difference. So once you have this piece done, everything else there is just a calculation. So from there you can write it in this form, and here's the gammas which are playing the role, the same gammas that are over there. There's an absolute value sign over here. This becomes a linear term, this becomes an absolute value term, this becomes W transpose. You're minimizing with respect to W and B, you're maximizing with respect to gamma. Because gamma lies between -1 and +1, I've just put that absolute value of gamma should be less than or equal to 1. Using the saddle point theorem, you can switch them. So basically what I've done from here to there is I've taken the max outside, put the min inside, and then solve it, and they do it exactly the way we did it for the singular value. The optimum choice for W is given there, and now you put the W back in there and you get that answer. This is not quite a quadratic program because of the absolute value term. You can transform this into a normal quadratic program by just replacing gamma as u minus v, and absolute value of gamma is u plus v, where u and v are greater than or equal to 0, and you'll get a quadratic program for that. What would a kernelized SVR look like? Anytime you have over here, the kernelized SVR would simply be that product looks like gamma I gamma j xi transpose xj. That's what this term is. So instead of that, you replace this to gamma I gamma j k xi xj. So instead of this gram matrix, you have that gram matrix that comes from the kernel. That's the only change that happens. Everything else is automatic. All right? Okay. So those are that. Okay, now let's switch to showing you some codes for PCA. Here are some examples. These are some, let's see, are these reasonably visible? Should I make it a little bit bigger? Yes? Question? No. Okay. Here again, I am just doing PCA of various kinds. I'm trying to figure out, just to give you a feel for what is happening. From scikit-learn, I'm getting digits data set. Digits are basically digits from 0 through 9. We are trying to find the size of the data set. It's 1797 by 64. Then what I did in this command over here, I did a PCA from to 2 dimensions. So here, this 2 inside there just says that find me a PCA just keeping the first 2 eigenvectors in, or first 2 singular vectors in the set. So when the projected PCA is, what this basically tells me is, this is a command that defines a PCA object where you're projecting from 64 dimensions, which is the dimension of the digits, back to 2 dimensions. Projected, which is PCA.fit transform, takes the digits data that I had and converts it back into a 2-dimensional object. So if you look at the digits.data.shape, that's 1797 by 64, which is the, better put this here. Yeah, so this one, it's printing the size of the original, this one is printing the size of the other one. And this is just fancy ways of projecting the whole thing. So now what I'm doing is I'm plotting component 1 here, I'm plotting component 2 there. The digits go from 0 through 9, and there are different colors being used. So if you look at what's happening in this space, you kind of see that different digits go sit in different places. So by just looking at 2 components of the PCA, you're starting to see that things are separating out. And if you want to play around with a little bit more, you can go and start looking at, so what happens in this confusion zone of the greens and the reds and the blues seem to be very confused over here. So you can go back and try to look what that is. So green is 5, red is 8, and blue is I think 2. So 2 and 5, hopefully there are no dyslexic people who are writing the reverse, I don't know. But 2, 5 and 8, there seems to be some confusion, and one can try to add more components to see what is going to happen. But this is a nice way of looking at it. So the reason I put down these codes there is that if you're looking at this scikit-learn kind of story, it would be nice to show, again, part of this exercise of data analytics is also to be able to visualize things correctly. And the whole reason you're doing PCA is to be able to see what is going on, and here it's trying to separate out the various points and saying where they lie. A very simple exercise. Yeah?
Consider that you are considering some case recognition.
Which will come in a little bit later.
How do I convert that case into that column format? Is some other software we have to use that will convert this?
That's almost standard. In most of these software, MATLAB, Python, there is a simple way of just, or even if you don't want to do it in another, you can write a simple code that just takes column buys and just stacks them into a vector. So take the entire, so take a, let's say you take a grayscale image. It's a matrix. You stack all the columns.
That is simple. Function is there.
There is a function in MATLAB. There is a function in Python. There is a function. You can write your own function. It's not a very big deal to do this. And in this particular case with PCA, in scikit-learn, when you do PCA, it doesn't even differentiate between vectors and matrices. It just counts them 1, 2, 3, 4, 5, 6 up to n plus 1, n plus 2, n plus 3, and keeps on going. So it's not even making a distinction. So this one you can just send in the matrix as it is. Like for example over here, I did not do any transformation. Scikit-learn's PCA assumes that if you're throwing it a matrix, you don't care about the matrix character. It's just your way. You happen to like to arrange the data in a square shape or a rectangular shape.
Then you have to define that array. It's taking means it's taking the array
And give you back the array. It doesn't care. It says, okay, you like to look at the data in this form. I will internally just do my PCA and return back the data in the same form that you like. That's all. I will see some examples where this will become more clear.
Sir, will you take most high priority?
Sorry, I couldn't get your question.
Will you take most high priority dimension from 64?
Could we just keep it down a little bit? I can't hear back there. Yes.
2 dimensions you are taking from 64.
Yes.
Will it be high prioritized or?
Oh yeah. So this, when you say 2, it takes the highest singular values. The highest singular value and the next highest singular value automatically. Yes. So here what we are doing is looking at, so here I'm not specifying how many digits that I want. I'm simply saying take the digits data, return for me the PCA. And here I'm plotting the cumulative sum of the PCA explained variance ratio. So explained variance ratio basically returns for me what is the what is the proportion of the variance that is being explained as you go along. The number of components is down here. So 64 is the maximum number of components. So that's over here. This is the cumulative explained variance, which starts from nearly 0. Oh no, there's some part of it. I don't remember exactly why. They should be around almost 0, and then it keeps going. So at around 2, we have only explained about 30% of the variance. And it comes up, and I think it's 12. Later on, I'll take 12 components, and that gives you about 80% of the variance. And this is a plot. Based on this plot, you can decide where you want. It doesn't look like this plot has actually very well-defined places. Depending upon what you want to do with the digits later on, you might have to work and figure out what to do there. Here what we are doing is just using PCA as noise filtering. Here are the few digits from that. It's an 8 by 8 digits. That's why you have a 64 pixels. So the size of this data set is 64, and the reason it's 64 is because these are 8 by 8 digits, or 8 by 8 pixel by 8 pixel digits. So these are just a top few digits that are there. So 1, 2, 3, 4, 5 up to 9. These are different samples of those same digits. Next, what I did was I added noise, a speckled noise to this data. So this is what the noisy images look like. And what we want to do now is to use PCA to be able to denoise this image. And the idea behind that is that the small amount of noise that has been added will add some corresponding singular values or eigenvalues, the way you want to look at it, but those will be smaller compared to the remaining eigenvalues or the singular values of the data itself. So if you chop off the small singular values, you should be able to get results which are better. So here what I've done is this is another way of doing the same thing. So PCA, now instead of looking at defining the number of components that I want, I've asked it to pick up 50% of the variance. Give me a PCA so that it gives me 50% of the underlying variance. The number of components that it picked up was 12. So for this noisy data set, if you want to explain 50%, you need about 12 components. Now from the noisy, so what does noisy stand for? Noisy is this, I have added, on the digits data, I have added a noisy data in there. So that's what that is. Filtered is PCA inverse transform of the components. So I take the components, which is PCA transform of the components, and then from the components I get back what the filtered images look like, and this is what the filtered images look like. So all the speckled noise that was there all around these images, all these little dots that have got nothing to do with the numbers themselves, have disappeared. They have been cleaned out. So if you take about 50% of the images, they start to look like digits again. Is it exactly the same as that one? Pretty close. Not exactly, but pretty close. Okay. Let me actually see something else. Here are some example that has been given from eigenfaces. There's a data set called, I don't know what this LFW people are. I don't know why they are called LFW people. Looks like there are a bunch of politicians. Ariel Sharon, Colin Powell, Don Rumsfeld, George W. Bush, Gerhard Schroeder, Hugo Chavez, Koizumi, Tony Blair. It looks like they are basically a bunch of, so the target names, these are the names. So it's basically picking up all the people for which the number of faces that we have is about 60. So we have 60 faces for each person. The target names are here. The faces, these are the images, the shape of the various images that you have. Now we are doing a PCA on that. We have first defined the function PCA. What this function tells you is that you should use a randomized solver, and the number of components that you're going to keep is 150. So you want to look at the comparison, each of the faces, the shapes are 1348, 62 by 47, and therefore the 62 by 47 is the image size. So you're just keeping 150 components, which is pretty small. In this randomized story, what happens is that in order to make the PCA solver faster, you can randomly guess what the output shape would look like, or output, not shape, but the output range is going to look like, and it makes it a little bit faster. And if you end up generating the SVDs, that's what the SVDs look like. If you stare at these, can you start picking up if there are any eigenfaces that correspond to particular politicians? This guy sort of looks like Bush to me. And then there should be some Colin. This guy looks like maybe Ariel Sharon, maybe. It looks like for the most part a lot of Bush dominates. Again, this tells you, if you look at 150 components, how much variance is being explained. So in this particular case, if I keep 150 components, almost 95% of the variance has been explained. So you don't need more than that to figure out what is going on in this data set. And now what we've done here is reconstructed their images. So this is the full dimensional input. This is the 150 dimensional reconstruction. And you can basically see again the same story. You solve it, you fit it on the faces data, you get the components, and you take the inverse transform, inverse PCA transform to get the projected. And what all that has been done is that first you have 62 by 47 is the size of each image. So first set panel just displays the faces data. The second panel, which is also 62 by 47, does the projected data. Projected is the one that was constructed by taking 150 PCA components. And the way you want to think about this is the comparison point that you should have is just to get you some comparison. 62 times 57. So it's about, each image is about 3,500 dimension. We have reduced the dimension from 3,500 to 150 because we have kept only 150 PCA components. So that is the reduction in dimension that has happened. And if you see, even after that reduction in dimension, you've got about 95% of the variance being explained. And that's what's going on over here. You can, for the most part, at least at the image level, for the human eye, they look pretty much the same. Maybe the contrast ratio is a little bit higher on the other image than compared to the bottom. It looks like contrast has gone down a little bit in the bottom one. Okay. Actually, I want to look at this one. I want to show this we haven't done, but I want to just show you because the same story happens here as well. Show you both of them here. What we are doing is remember in the lecture we were talking about Olivetti faces. This is one of the standard face recognition data sets. So this experiment is on Olivetti faces. It shows lots of different classifiers. So these are all very built in. So eigenfaces, this is using PCA, using randomized SVD, non-negative matrix decomposition. This is again something that you can do. This is independent components analysis, mini batch sparse PCA, dictionary learning, mini batch k-means, decomposition factor analysis. All of these things are actually built into scikit-learn. So you can essentially bring that all out, and with just giving a simple command you can start constructing what these are the eigenfaces. These are the non-negative matrix composition. If you look at them, this is independent component analysis, sparse PCA, and now you start seeing that if you compare the sparse PCA with PCA, you start to see the advantage of putting sparsity constraints. In the sparsity, in this particular case, it's not really taking, it's basically saying that you take the mask that you put on the image is pretty large. It lives on all the entire space. If you force on sparsity, then you get that. And it seems to be picking up some features. So it picks up eyes, it picks up some chin-like structure, nose there, eyebrows, and you're starting to see that perhaps these are the features that are responsible for generating the images. Dictionary learning. So what do I want to show you? Why did I want to show you this? So remember in the notes we said that both sparse PCA and dictionary learning are trying to get at sparsity. But the dictionaries that you create are very different. This one actually tries to find some features. This one is an over-complete structure where you're saying that I want sparsity in how the reconstruction happens, but the factors themselves, the factor loadings themselves need not be sparse. This is a k-mean clustering. This is equivalent to vector quantization. So these are essentially the faces that are somehow the centers of the population of faces that you have. And now, I don't know who this person is, but they pretty much picked up the entire face. This is factor analysis components, and same thing of various kinds of different colors, and they should be somewhere at the end. No, it's basically the same thing. So here, positive dictionary and code. This is where you do dictionary learning and you put a positivity constraint of various kinds. So the only thing that I wanted to show you here is that once you know the theory of what is going on, all these things are already coded up, and so you don't really have to worry about doing the stuff. What you need to worry about is what is the right methodology to use. Unless you're looking at a data set which is so huge that you can't really put it into Python and call various things, most of what you want to do is clearly available right there, and you don't have to worry too much about it. Okay, what else do I need to show you here? Okay, this is another example of PCA-like thing using for classification of face recognition. Again, I'm getting this LFW. This is the politicians' faces. Now I'm picking up all those people for whom at least 100 images are there. Split the thing into a test set and data set, test and train set, and I took 70% of the data as test, 30% of the data as train, computed a PCA, which kept 100 components. And I did this PCA on the training set, which has about 70% of the data, applied the PCA transformation both to the training set and the test set. And this time I decided to be a little bit funky and basically called a neural net to train on the images. Again, the only reason that I wanted to show you here was the fact that once you get into one of these situations, you can basically call these various solvers and see what happens. This is the hidden layer size. That's the batch size that I'm using. Verbose, it's going to type out various things, and it's going to try to classify using X-train PCA. So this is the X-train images have been converted into a train PCA. Y-train is just a label about whose image it is. You just fit this. It's fitting the classifier to the training set. It's look at various the losses of various kinds. Validation score did not improve after 10 consecutive epochs, and they're stopping. It just tells you what the answer is. And here what you're doing is you're predicting on the test PCA, Y prediction, and then print the classification report. F1 score is, I forget, it is 2 times precision divided by, it's like the harmonic mean of precision and recall. So yeah, so 1 over F1 is equal to 1/2 of 1 over precision plus 1 over recall. Yes?
Can you move to the neural network?
Yeah.
You can like hidden layer.
Yeah.
So how to define hidden layer size? Because
Just a guess.
is there any
Formula? No.
because most of the papers they do it by hit and trial method.
Yes.
By
Classified.
hit and it's like the one which reduces the error.
Yeah. Everything is cross validation. There is no method.
So there is no method to
No.
decide this hidden layer.
No. So that's basically what you end up getting for the F1 scores of and this is a visualization. It's not very clear. I'm trying to see whether there's any error that was created over here. Bush. This one. For this picture, it predicts Bush, but the true label is Rumsfeld. Politically, they are okay. If I this one also is an error. Predicted is Bush. You can't see it very clearly, but the true is Blair. So it must be that the number of Bush images are very large. Let's just check. Yeah. So 149 Bush images, and that's probably why most of the errors happens with predicting it to be Bush. Okay. So all these codes, you have it. You can play around with it and see what you can do with that. All right. I want to go to the lecture notes at this point, so maybe we can take a break now.